Today we're looking at visible light, section 16.1, and I have the lighting in a very different way today because I'm going to be doing a quick demonstration for you guys. And we're going to be doing part of the lecture, and then I'd like you to take a break and then do one of the labs. And then after the lab, we'll come in for the conclusion of the lecture. Then I'd like you to do the second part of the lab. I think it would fit quite nicely with that. So we're going to go ahead and take a look at visible light. And if you remember from chemistry, we've done some of this before. And so it might sound a lot like review. But if you remember, visible light contains the colors of the rainbow. So we have all the colors of the rainbow. If you remember the acronym, it's ROY, G, BIV. Red, orange, yellow, green, blue, indigo, violet. But oftentimes, this is reversed, and I'll share with you why it's reversed, and it is going to be VIBGYOR. So we have violet, indigo, blue, green, yellow, orange, and red. And beyond the red, what we have is called IR, or the infrared light. And beyond that, we have microwaves. Going backwards, this direction from the visible light, we have the ultraviolet light. So the visible light is actually within this range right here. It does not include the infrared because we can't see infrared. We have technology that can see infrared as heat, but our eyes cannot detect it. We have technology to see ultraviolet, but our eyes cannot detect the ultraviolet light. It's beyond our vision. So we're going to be focusing on this range, and why is it put in this range in particular? Well, because this is how it's measured. These colors of the rainbow of the visible light, so here we have the visible light, we have these colors, and these colors are measured by what's called their wavelength. And if you remember, wavelength is the length of the wave from chapter 14. And it ranges from 400 nanometers all the way up to 700 nanometers. Okay, so these are the lower wavelength, but these also have, if you remember, wavelength and the frequency are inversely related. So these have a lower wavelength. Let's go ahead and put this down here. We have c, which is the speed of light, is going to be equal to the wavelength times the frequency. So if we have a lower wavelength here, that means we're going to have a higher frequency. We're going to discuss this in our first lab very, very soon. So if this has a lower wavelength, this is going to have a higher frequency. And over here with the higher wavelength, this is going to have a lower frequency. We're going to see how this relates to energy as well. So which has more energy? Which can harm your skin more? Visible light or ultraviolet light? The answer is ultraviolet light. Well, why does it have harm your skin more? It's related to the frequency, but these also, the lower wavelengths, have higher energy. So this has higher energy. The ultraviolet light has more energy than the visible light, and then your infrared over here has the lowest energy. And again, we'll see that in a lab very, very soon. So here's our introduction to light on the visible spectrum, which is part of the this electromagnetic spectrum, which includes radio waves, it includes X-rays, it includes gamma rays, and all that. This is part of the electromagnetic spectrum. So let's take a look at the two properties of that light have. So we're going to be looking at the properties. One of the properties of light is that it can be measured in a wave. We're talking about wavelength here, and so light occurs in waves. So light is said to have these wave properties, which again is measured in wavelength. And wavelength again is going to be this Greek letter lambda. We'll get into some calculations, but these waves are measured in nm, nanometers. measured in nanometers. And we'll just put in parentheses, nanometers. And to remind you what a nanometer is very, very small. If you cut a meter into 1,000 parts, you have 10 to the minus 3 meters, you have a millimeter. If you cut that millimeter into 1,000 parts, you then have what are called micrometers. 10 to the minus 6 is micrometers. Nanometers is the next order down. It's 10 to the minus 3 below that. So 1 nanometer is going to be equal to 10 to the minus 9 meters. Very, very small. So we have 1,000 millionth. This is a billionth of a meter. This is the order of magnitude that light waves are. So if light has a property of waves, then they must bend. If you remember, we did this wave plate, or we had the Jenga pieces, and we had these blocks. So these are the Jenga blocks, okay? And if you remember, we sent the wave through these, and the wave actually felt these sides. This was a barrier to the passing of the wave. And so we have what's called diffraction because of this, because of a barrier. And what happens is when it passes through these slits right here, if you remember, we got this bending of the wave. And the wave continued to go out like this, and then what we saw were these ripples, and these ripples were overlapping, these concentric rings were overlapping, and they're creating these spots of peaks and troughs. Well, right here, where the two waves converge, this is going to be constructive interference. And where we see constructive interference, this is going to be amplification of the wave. So we see this wave amplification, and in other parts, we see a wave cancellation. So what I want to show you is to show you that light actually does has these properties. What I have is I have a screen here, and it's very, very thinly made with polymers, and these polymers are aligned all in the same direction, and it's going to be acting as a barrier to this laser light. So let me go ahead and turn the volume of the light down so you can kind of see this. So here is my laser light, and here is this, and this is going to be my screen. This is what's going to be causing the diffraction of these waves. It's going to be a barrier, so we're going to have the bending of these waves. So I'm going to now pass this light through the barrier, and we'll see what happens. So we get a separation of this, and this filter, again, is acting as a barrier, and it's creating these very, very narrow slits for the light to pass through, and that causes the light to bend and create this ripple effect. And there are these areas right here that we have amplification, and so that's what we're seeing. We're seeing this amplification effect, and that's what we're seeing with that. So this is a piece of evidence showing that light is a wave. It has properties of a wave. One of the other properties of light is that it's a particle. And what I mean by a particle is that it is going to be a packet of energy. This is called a photon. So light is both a particle and a wave, and they have what are called photons, and these photons are packets of energy. We've discussed this previously when we were talking about neon lights. And if you remember, if you have your atom, And so here's your nucleus of the atom, and here's your electron shell. What happens is you can take an electron and excite it. So if this is the electron, we can then excite this electron to go to a higher state. And we can do this with a photon of energy. This photon or particle of light can go into an atom and cause the electron to jump up to the higher state. So if you remember, the photon is a packet of energy. So what we're doing is we're supplying this electron with energy. So the electron gets excited. So we have this excited electron, which jumps up to the higher state. So the photon comes in, we got the excited electron, it's spinning around its shell, but then it falls back down to the lower state. And again, as it falls back down to the lower state, the energy is going to be released as light. So we're going to take a break from lecture, and we're now going to go to the light as a particle lab.